Welcome to this video for the advanced higher physics topic of electromagnetism, and this is looking at electromagnetic radiation and some of Maxwell's relationships. So these are the things that we're going to briefly discuss in this video. The unification of electricity and magnetism by James Clerk Maxwell. Reinforce that we can tell if something has wave-like properties from what it does, refraction, reflection, diffraction, interference. We describe electromagnetic radiation in terms of their electric and magnetic field components and carry out calculations using the relationship C equals 1 over the square root of epsilon naught mu naught. So firstly, a little bit about James Clerk Maxwell. So here's some pictures of him. He was born in Edinburgh and he is recognized as one of the most influential scientists for physics. Einstein himself acknowledged that his theory of relativity lay in much of the foundations that James Clerk Maxwell did. There's a statue of him in George Street in Edinburgh with his dog. But even though he looks quite old there, you can see that he actually didn't live to be particularly old. So Maxwell's research into electromagnetic radiation and linking together electricity and magnetism has led on to the use of electromagnetic radiation for communications. Richard Feynman from California, American physicist, put him down as one of the most significant event of the 19th century. So we've already learned in this course and at higher that there are 4 fundamental forces: the strong, the weak, gravitational and electromagnetic forces. And it's James Clerk Maxwell who unified the electricity and magnetism into a single theory of electromagnetism. We're still trying to unify the other forces into in our standard model into a grand unified theory, and we've not completely managed to do that so far, but he managed to link those two together. So he showed that electromagnetic radiation exhibits wave-like properties and that they travel at a fixed speed, the speed of light, and that they're made up of oscillating electric and magnetic fields. For simplicity, we usually just show the electric field, but both the electric and the magnetic field are oscillating in phase at right angles to each other and to the direction of the energy propagation, the way the wave is moving. And Maxwell predicted electromagnetic waves mathematically before there was any evidence of their existence. So we can see at the bottom a picture of our electromagnetic waves. So usually we just show the electric field oscillation, but there is also at 90 degrees to that the magnetic field oscillation, which is in phase, so to that one. Maxwell's relationships predicted that electromagnetic radiation should have a constant speed of the speed of light, and this arose from a combination of 2 other fundamental constants that came from his earlier work looking at electric and magnetic fields. And he saw that the permittivity of free space, epsilon naught, sometimes known as the electric constant, and the permeability of free space, mu naught, the magnetic constant by some, and he saw that these 2 were actually related to the speed of light. So the speed of light is equal to 1 over the square root of the product of epsilon naught and mu naught, the permittivity of free space and the permeability of free space. So we've got a relationship between 3 fundamental constants. If we look at this relationship and we look at the units, we can delve into a little bit to see that they're consistent with meters per second being the correct unit for the speed. So we've got farads per meter times henries per meter, but we can have capacitance, farads, as charge per volt, because C equals Q over V. We can have henries as volts times seconds per amp, and we can multiply those together, and you can see that when we end up at the end, we've got meters per second for our units for C. Okay, you don't need to be able to do dimensional analysis, but this is something that physicists and engineers do quite frequently to look at the dimensions of particular units and quantities. Okay, the speed is not measured relative to anything, so it's fixed for all moving observers. And this ended up being one of Einstein's postulates for a special theory of relativity. The speed of light is actually not quite 3 times 10 to the 8 meters per second. It's only 299,792,458 meters per second. And since 1983, the meter is now defined as the distance light travels in a particular interval of time. It used to be that there was a fixed meter length of material, but now, because that changed slightly with temperature, although they can pick materials that don't change significantly with temperature, but it was changing a little bit, so the meter is now defined from the speed of light. What we've briefly discussed in this video is James Clerk Maxwell linked electricity and magnetism to electromagnetism, that electromagnetic radiation can behave like a wave in terms of interfering, diffracting, refracting, reflecting, or we will also know that it can behave as a particle through the photoelectric effect, and that we can describe electromagnetic waves as our transverse waves, and we can now talk about the electric fields and the magnetic fields, which are both at 90 degrees or perpendicular to each other and oscillating in phase. And we can carry out calculations using the relationship C equals 1 over epsilon naught mu naught, or the significance of that being the speed of light.